Welcome to Section 3, Natural Language Processing, or NLP, and Recurrent Neural Networks, or RNNs. Nearly all neural networks that process language contain one or more RNNs. More generally, RNNs are useful when our data is inherently sequential in nature. When processing text, we want some way of capturing the fact that the order of the words is important, and we'd also like our model to handle text sequences of variable lengths without needing to change its number of parameters. RNNs are great for such situations, and we'll see many examples of how to work with RNNs for natural language processing tasks throughout this section. The section will consist of 5 videos. The first 3 videos will cover foundational concepts seen in many applications of NLP with deep learning, embeddings and recurrent neural networks, or RNNs, and more advanced RNN architecture variations. Having a solid understanding of these topics will allow you to tackle many applications. The final 2 videos will work through the common task of document classification. This is similar to the image classification task we saw in Section 2, except for now we're training networks to predict labels given documents of text instead of images. We'll start with the basic RNN implementation and then move to a more advanced version that will test everything we've learned so far. Let's get started. Today's video is on the topic of word embeddings. Word embeddings encompass the general technique of converting words into a numerical representation, most often assigning a fixed length vector to each word. We'll begin by providing a general overview of the ideas behind converting words into numerical vectors. Then we will learn about one of the most popular algorithms for learning word embeddings, called GLOVE, short for Global Vectors for Word Representation. Finally, we will see the utilities available in TensorFlow for working with word embeddings. Recall from Section 2 how we represented images as a grid of pixel values, which were fed directly to our convolutional neural network. What if we want to feed human language as inputs to our neural network? There isn't an obvious representation as was true for images. To visualize the general process that we'll soon become very familiar with, consider the sentence, "I like dogs." First, we'll want to separate sentence into the individual words, a process called word tokenization. Now we need to find a way to embed these words, or convert them into a vector of numbers. We also want similar words to have similar vectors. We usually measure how similar 2 vectors are by some measure of the distance between them. We'll see one algorithm for doing this in the next slide, so don't worry about the details quite yet. We're just getting a general feel for the process right now. Now these are ready to be fed to a traditional neural network. In this section, these will always be fed to a recurrent neural network, or RNN for short. We'll be covering those in detail in the next video. There are many approaches for learning word embeddings, and one of the most popular is GLOVE, short for Global Vectors for Word Representations. Although it is true that we can just randomly initialize our embeddings and learn them from scratch with the rest of our neural network parameters, it is more common to use pre-trained embeddings that are trained on enormous text corpora of billions of samples, so that way our neural network can focus on learning the other parameters without needing to worry about learning a good vector representation of each word. When we make our document classifier in the final 2 videos of this section, we'll load pre-trained GLOVE embeddings for our embedding layer instead of training them from scratch. It's always a good idea to have an understanding of any pre-trained model we load, so let's see how these vectors are learned in the first place. First, some terminology and notation. Consider the very simple case where our entire corpus is just one sentence with 4 tokens, "I like dogs," and the period. Let's say we are considering the word vector for the word like. We say that the context of the word like consists of the words on either side of it, if we define our context size to be 1. If we define our context size to be 2, then we consider the 2 words on either side of it, or up to 2 if there are less than that on either side, as is the case here. And so on and so forth. With that general idea in mind, we can get a general understanding of the loss function that GLOVE uses for learning word vectors. We train the values of each word vector, of which there are v total, such that the loss function here is minimized. From left to right, we can read this loss function as follows. The summation tells us, loop over all possible combinations of words out of the set of unique words that occur in our corpus. For each such pair, compute the inner product, or dot product, of the vector for word I with the context vector for word j. Note that for any given word, we learn 2 distinct vectors, the main or current word vector and the context vector. This is why the context vector is shown with a tilde, and I've written them in different colors to further remind us that they are distinct. Without going into too much detail, a core component of the GLOVE model is the hypothesis that words that frequently occur near each other are closely related. Mathematically, one could model this assumption by saying, we expect the inner product of 2 words to be related to the probability that they frequently occur next to each other. In a nutshell, that is what motivates the subtraction of log p sub ij. Remember that if you want to minimize a term containing some value minus another value, you want to make those 2 as close to each other as possible, and that is our goal here with the GLOVE model. We want word vectors such that similar words have large inner products and hence are closer to each other. Finally, you may have noticed I skipped over this function f of pij. This is a weighting function of the word co-occurrence probabilities that looks like the image on the lower right. Its entire purpose is to give more weights to word pairs that occur frequently together than very rare pairs, since we care more about getting frequent pairs correct than ones that hardly ever occur at all. In the interest of time, we've had to cover this material extremely fast, and if you'd like to learn more about GloVe, I strongly suggest you read through the additional resources links in the final slide. Remember that it's not absolutely required for you to understand the details of this algorithm, since in practice, we'll just be loading the pre-trained vectors from a file and moving on. The main takeaway is that we want to train our word vectors such that similar words have similar vectors, and dissimilar words have dissimilar vectors. Okay, that's enough theory for one video. Time to move on to coding. We'll now work through an example showing how to load GloVe vectors into TensorFlow layers and train a simple autoencoder using these vectors. An autoencoder is a simple model that is trained to output whatever is fed in as its inputs. Another way of saying this is that an autoencoder is trained to reconstruct its inputs as its outputs. Although this may sound like a strange task, autoencoders are useful for a wide variety of tasks. Our purpose here isn't to learn about autoencoders, however, but rather to focus on how we load and pre-train GloVe vectors into its first layer. Okay, we begin with our main function here. We begin with some pre-steps that are pretty straightforward, like defining file paths and vocab paths. The first real step for us is to prepare our data. Although the GloVe vectors we'll be loading contain all the information we'll need in our layer, we do have to do some pre-processing first so that it works well with our training data set. So I'm going to be using what's called the 20 newsgroup dataset, which we will learn about in detail in the last two videos when we're doing classification. For now, all that really matters is that it consists of sequences of text, and those are the text we want to extract from the dataset, and we want to tokenize that, we want to count the words in it to create our vocabulary, all these things that need to be done before we can actually get to the TensorFlow part. So that's actually the very first thing we do in our main function. Is I have had this thing called ngutil for newsgroup utility, and it's fit and extract, and it looks like it returns to us a vocabulary, which is actually a list of the words, the most frequent words from most frequent to least frequent, the labels, and text for that training data set. So let's see this important pre-processing step that we'll need anytime we're working with word embeddings and we need to set up which words we're most interested in. When I say most interested in, consider the fact that a training data set is going to contain sometimes millions, even billions of different words, and we can't possibly expect to load them all into a single layer and train them on our computers. So we need some way of picking out words that are most important. Well, one of the easiest ways of doing so is just doing the most frequent words. So typically, as this function does actually here, we will count how many times each word in the text occurs. We'll pick out the top most occurring of them. Usually we'll call that our vocabulary size. I default that in this file to 10,000. It all depends on the hardware you're using and how much you can handle to process. So what this function does is it will loop over each line from the newsgroup file, which is a text file. We'll have the label and the text for each line. So first we want to tokenize this line so that we get the individual word tokens, and then we count. We increment our counter for each token on that by 1. So the whole purpose of this loop here is collecting the word counts for our training corpus. We will then loop over the words that we've collected in our word counter, and we will take only the most common, only the vocab size most common. Note that I'm subtracting off what's looks like here as our start vocab. Start vocab is some number of special tokens you want to prepend to your vocabulary, and in this case what we'll be doing for our start vocab is a padding token and an unknown token. So the unknown token will be what we replace every word that we see that isn't in our vocab size list. The padding token is used to make sure that each tensor we feed in as a batch to our model has the same number of tokens inside of it. So if we have, say, a batch of size 2, one example in that batch contains 5 tokens, and the other one contains 7, we will pad that to size 7, so we'll add 2 padding tokens to that sentence. Now we have our vocabulary list, our labels, and our tokenized text, and we are ready to move back to our main function. As an intermediate step, I am saving our vocabulary for access to later, should we want that. And I also do a conversion from our text format to a TF records format. TF records is a binary format that works really well for inputs to our model. TensorFlow, this is actually a native TensorFlow format, and it works with TensorFlow protobufs. Protobufs are something that we're going to go see in the production section of this course. For now, let's just look at this as saying we're going to save this, convert this format to a different file format, which is easier to load with the tf.data module, because tf.data has the tf.data.tfrecords dataset. Again, more details to come in the section where we cover protobufs, but for now, just know that we're saving the dataset in a different format for easier loading. Okay, now it's time to go and create our model. So this is the autoencoder model, and we feed it the model function. Again, the main part of defining any estimator is its model function. As usual, we have our model function with features, labels, mode, params. Here's the most important part of this function where we actually see how the glove vectors are loaded and interfaced with TensorFlow. So let's see, I have this function glove embed, and that's going to give us our embedding features. So let's see exactly how this works. It'll be very important that we pay close attention to this portion. So first, we actually just read the glove vector from a file. So I had this utility function called getGlove. We can briefly go over this here. All it does is load from our data path. I will provide these glove vectors. You can also just download them from stanford.edu. Stanford is the original source of the glove vectors and the idea of glove in general. Once you have the glove files, you'll see that each line consists of a word, followed by a space, and then what follows is its vector. The vector will be a fixed size, and it will be given by the file name. So some of our options are 50-dimensional, 100-dimensional, up to 300-dimensional. So when we return from this function, we'll have a dictionary of all words this glove model was trained on and the corresponding vectors. And this is going to be much larger than the vocabulary size that we've specified, so we'll be narrowing this down inside of our main function. So we have our word to vector dictionary, and what we're going to do now is the step of building up our layer for initialization. So we're going to have what's called an embedding matrix, which I'm going to initialize to a matrix of 0, and it's going to have shape, embed shape. Embed shape was the input to this function. And if we look back to our model function, we set this embed shape to vocab size by embed size. Vocab size, up to us to specify what that is. It's usually around 10,000, as much as your GPU can handle. And embedding size, we're a bit more restricted here if we want to use the pre-trained vectors, because as I said, our choices here, I believe, are 50, 100, 200, and 300. So we choose one of those, and so that's the fixed length vectors of each word that the glove was trained on. Now we take a loop over our vocabulary. So this is the vocabulary, the list of all words that we wish to be training on, the ones that were the most vocab size occurring, most frequently occurring vocab size words. We want to extract the vector for that word. So we take our word to vector dictionary, we get the word, and so long as that word was actually in our word to vector dictionary, we set the index given by the vocabulary to that vector. Note that this is kind of an implicit definition here. So we have a vocabulary list, and for the ith entry in the vocabulary list, we are going to identify that word as having index or ID I. This is a very common way of associating words with a single integer value. So there's a lot of mappings going on here. You have the single integer ID for each word, and each word also has a vector, a float vector. So it can be a bit confusing to get used to, but remember that the main motivations for these are we have a list of words, the most frequently occurring ones. Our ultimate goal is to convert those words into individual vectors, but also we need to make a decision of how to organize these words inside of a layer for a neural network. So we need to associate them with indices. That's a requirement. So the easiest way to do so is to sort them by most frequently occurring and just assign sequentially from there. So aside from our start tokens that we initially put in, the ith word in our vocabulary is the ith most frequently occurring word. In our case, it's more like the I-2 most frequently occurring word, but that's the gist of it. Next, we define our embedding tensor. So this is more or less just converting that matrix that we just built up into an actual TensorFlow tensor. We give it a name, and our initialization here, important, we're initializing it to the embedding matrix. So TensorFlow allows you to simply initialize your layer with a matrix of your own that you've defined, so long as, of course, that the shapes match of that embedding matrix with the one you're trying to create. And a very important part here is that we set trainable equals false. Remember that every variable created in TensorFlow is assumed to be trainable, but we don't want to train this variable because we've just loaded pre-trained vectors into this, and it's important that we keep them at the fixed state that we loaded them in. Okay, so now we have this tensor. That doesn't really tell us how we're going to be converting our words that we're feeding into this model into actual inputs to our neural network, does it? Now the magic really happens with this tf.neural.net embedding lookup. So what it expects is this tensor of lookups, or the lookup table, and we're going to be feeding it features. The features that we feed it are actually just going to be a sequence of word IDs. The IDs correspond with the word IDs that we just discussed previously. And what TensorFlow does is it has an efficient operation for converting sequences of word IDs into tensors by doing lookups on the rows of this embed tensor. Now the details of that are actually a bit involved, and there's different modes that you can set this thing on, but the defaults are what we're looking for. And for the purposes of this course, this is perfectly sufficient for loading in our glove vectors. So now we have our embedded features, and this will accept word IDs as its inputs. The rest of our model function is more procedural, straightforward stuff that we see repeatedly whenever we're defining a model function. More or less, I'm just defining the rest of this so that we have some model to work with here. First, I give a hidden layer after the embedding one. This hidden layer will contain all the learnable parameters for our model. It's because it's going to actually stick with the pre-trained glove vectors. And in order to learn how to reconstruct its outputs from those, it's going to tweak the parameters in this layer alone. From there, it's going to project out to its vocabulary size for trying to reconstruct the outputs with logits as usual. We're going to revisit this predict mode in just a bit. Right now, we're going to be focused on training. For our loss, as is oftenly done, we use the sparse softmax cross entropy function. And our training operation, we let tf.contrib.layers.optimize loss handle most of it. We use the atom optimizer, which is great for working with recurrent neural networks. And we do the usual outputs and metrics just to evaluate our model, like accuracy and making the labels the same shape as needed for the outputs. Again, you'll have access to all these files if you'd like to look through them in detail, which I strongly encourage. Okay, so now we've seen the model function. Let's see how it's used. We've created it, and all we do is call its train method. We feed our input function with our data directory. This data directory is going to be the one that has the TF records data and the parameters for us to tweak our model. Let's take a brief look at this input function here. It is the same style of tf.data that we've seen before. So our input function is just going to call make batch of this small class I've called dataset here. Make batch is nothing more than it gets files names. File names for us is just the embed.tf records. It's very simple, kind of a toy example, if you will. We use the tf.data tf record dataset utility. This is the format that we saved it in. And then we do the often steps of parsing out the examples. We do a padded batch. We want all the batches to have the same length so that they're rectangular tensors. We do an iterator of the dataset, and our features are actually the same as our labels, because for every text batch we feed in, our goal is to return that exact text batch as output. Again, kind of a contrived example, but it's useful for seeing how the end-to-end process of working with feeding word vectors in. Okay, so we've run the model.train, so let's see what that looks like when we actually execute it. So here's an example output that I had on my machine. We get a huge amount of outputs from TensorFlow, kind of some diagnostics here, which aren't terribly important for us. It's going to loop over the steps, print out some metrics like accuracy. We see that it learns these words very, very quickly. Not too hard for this model to figure out how to, given one layer of very nice pre-trained glove vectors, how to reconstruct the outputs. And it ends after just, let's see how many steps we have here. Just 1,000 steps, I get 99.5% reconstruction accuracy on the training data set. So it's now to prove that it actually has learned how to reconstruct some number of its outputs. I have some sample sentences. The familiar I like dogs. I am a test sentence. TensorFlow is a fun library to use. And now we're actually going to see also how to use the predict mode for our estimator. So I'm just going to loop over here, and I'm going to convert each of these sample sentences into a tokenized integer IDs, because our model will only accept integer IDs, so we convert those with our vocabulary as we've done before. Then I feed those in using the very handy tf-estimator numpy input function, so I can just feed it directly in to get some quick predictions out. We call Autoencoder.predict, and the only difference with logic here is that we have to go into if mode is tf.estimator.modeKeysPredict, and instead of doing the rest of this model function, it'll figure out the probabilities from the logits, it'll get its predictions, And what's new here is using this utility tfcontrib lookup index do string table from tensor, a very verbose function. We feed in the vocabulary, so this is still just the familiar list of words that we've been using this entire time. And we can feed this into TensorFlow by this table. And what it'll do is given predictions, which are going to be integer predictions of the exact same format as the input sequence of IDs. And if, for example, the number 5 is found in predictions, it'll go over to this params.vocab list. It'll look at the 5th entry in params.vocab, and it'll get the word corresponding to that entry. And so we now have our predicted words, and we can return with the estimator spect. All that's required for predict is predictions and the mode. And that's pretty much it. I just loop over the predictions and print out the difference between what I fed in and what I got on the out to kind of qualitatively evaluate the performance. And let's see. So it was able to reconstruct dog. I like dogs, which is nice because that's our main sentence here. Now let's see a little bit deviations from that. I tried feeding in I am a test sentence, and it fed me I am a test guilty. So we have an error here where it looks like instead of sentence, it has output the word guilty. And we can sometimes kind of see why these words might be confused for a model that was trained so quick. My best guess is that sentence and guilty occurred in the context of law. So it saw the word sentence, and the vector representation of sentence and guilty may actually be pretty close in this embedding space. And because of that, it may have given it similar prediction probabilities, and it looks like guilty may have just went out by enough to beat the correct prediction of sentence. For the other one, TensorFlow is a fun library to use. I explicitly use the word TensorFlow because I know TensorFlow is probably not in that 20 newsgroup dataset, because I believe that dataset was collected before TensorFlow was released. And we do see that it reconstructed is a fun library to use, but it didn't do anything with TensorFlow. That's something I've done in the post-processing of the outputs, where any outputs that are unc or unknown, that special token, have been omitted, and that's exactly what happened right here. As always, make sure to read the links here for an in-depth look at the topics covered today.